Now, today we will be discussing electromagnetism. What is electromagnetic induction? In physics, I've mentioned this thing a couple of times that induction actually means abnormal way. The normal way to produce electricity is battery or cell or a voltage source. Because what is our belief, what is our conviction? Every conductor contains free electrons. Those free electrons are actually moving in random direction. So when they move in random direction, the net flow of electron actually becomes zero. The net flow of electron becomes zero. So what we need? We need to align all the electrons so that they will be moving in one direction only. And when electron moves in one direction, current is generated. And not only this, remember electrons always travel from dash potential to dash potential. Can you feel this?
Can you repeat, sir?
Now my question is, electrons always travel from dash potential to dash potential. Higher or lower, you have to fill it in correct order.
Higher potential to lower potential.
Think again. If we talk about electron travels from higher potential to lower potential or lower potential to higher potential. I mean, I have 6 students in the class. You people should think. It is pretty simple. I mean, if you look at a cell, electron moves from minus to plus. So minus means lower potential, plus means higher potential. So electrons always travel from lower potential to higher potential. Are you people getting it? Okay, Anas is getting it. Yes, Alan, Amna, Hania. So electrons always travel from. Yes, Amna, you were trying to say something.
No, sir. I just wanted to say that I got it.
Okay, so what you could have done, you could have just raised your hand as well, right? Anyways, so when we talk about electrons always travel from low potential to high potential. So I can say one thing. If electrons are flowing in one direction, one specific direction, let's say electrons are moving in this direction. So what I can conclude, this end is at low potential and this tip is at high potential because all electrons always travel from low potential to high potential. Now, this is something we should have in our mind because what I'm going to explain, if you have this point in your mind, you can understand it very easily. Let's say we have a magnetic field, and in that magnetic field, this is north, this is south. So we know that electric field is always from north to south. So I can draw electric field and I'm drawing electric field like this. From north to south. And this is direction of electric field of induction. It's a vector quantity, so I put an arrow on B. Now what I did, I took a rectangular piece of wire and that rectangular piece of wire will appear something like this. The rectangular piece of wire appears something like this. Now what I want you people to focus only on one specific length of that wire. So what I'm doing, I'm making this other sides dotted so that you can focus only on the side I want you people to focus. So we will be focusing only on this side of the conductor. Only one side of the conductor. It's a complete loop. I just want you to focus only on one side of the conductor. And I'm calling this side as A, B, C, and D. So I want you to focus only on side AD. Now this is a conductor. This wire, let's say this coil is made up of copper. Copper is a very good conductor. That's why in normal circumstances, when we look at the wiring at our houses, we make use of copper wire because resistance of copper wire is very small and it is cheap actually. So we can make wires from it. So this wire is made up of copper. It must be containing some free electrons. Those free electrons must be traveling in random direction. When electron travels in random direction, no electric current is generated. Let's do one thing. Let's try to pull this coil out of this magnetic field. So I will exert a force. This force F is exerted by me. So what I'm saying F is force exerted on coil. I'm explaining each symbol so that you don't get confused because we will be discussing at least 3 different forces in this diagram. So F is the force exerted on the coil. Now, when you exert force on the coil, what will happen? You are actually trying to pull the coil out of magnetic field. So when the coil is moving out of magnetic field, just look at side AD like this. Electrons were moving in random direction, but when you pull the coil out of the magnetic field, they were moving in random direction, but all the electrons will be traveling in horizontal direction as well. What I'm trying to say, just imagine this is magnified version of side AD. In this side AD, we have large number of electrons, and these electrons are moving in random direction. These electrons are moving in random direction. When you exert force F on the coil, what will happen? All electrons keep on moving in random direction, but they all will start to move horizontally as well from my right to my left, or in easier word, in the direction of F. Okay, let me repeat it again, then I will take your opinion if you are getting it or not. Let's say this is the conductor. Electrons are moving in random direction. Okay, you cannot see it. For example, look at it. Let's say this is a conductor. Electrons are actually moving it in random direction. This is side AD. If I pull the coil out of the magnetic field, so this conductor will move in this way. So electrons which were moving inside this conductor in random direction, they will remain random. But being random, they all will be moving horizontally in this direction. Do you people agree? Yes, Alan, Amna, are you people getting it? Okay, Alan is getting it. Amna, what about you? Okay, all of you are getting it. Now, when all electrons are moving horizontally, remember, when magnetic field sees charges moving in direction or moving in the magnetic field exerts force on the moving charges. So what will happen? Now, a force is generated, which is denoted by FB. FB means this is magnetic force, and it is given by QVB sine theta. We are talking about electrons, so Q is replaced by E, V, B, and I hope you will agree that theta is 90 degree because the way electrons are moving horizontally, field is up to down, top to bottom, angle is 90 degree, sine 90 is 1. So magnetic force is AVB. Now, what I'm interested in is actually the direction of this magnetic force. So I'm giving you 2 minutes. You will think of the direction. I will finish my tea meanwhile. Then I will take your answers. So what you need to do, you need to tell me what is the direction of FB, the magnetic force on moving charges or moving electrons. So just think of direction. I will join you back in 2 minutes. Yes. So did we conclude the direction? What will be the direction of FB? Yes. Any one of you?
Sir, into
What
the
what should
board.
be into the board?
Yes, sir.
Okay. What about others? What do people
Yes, sir.
think? What should
Yes,
be the into the board? Okay.
yes, sir.
Let me just try myself as well. Because the field is top to down, velocity is rightward, it should become out of the board. But this out of the board is for positive charges. So you mentioned this direction in the context of electron, right? Yes, Anas, Anal.
Yes, sir.
Okay. So the direction of electronic current will be into the board. The direction of electronic current will be into the board. So in fact, the direction of electron or direction of this force will be into the board. Now, what does it mean? I will explain. Let me mention the direction. And the direction of force is into the board. I hope you remember this thing. This cross will remind you this is into the board. Let me draw leftward arrow here. So it will remind you it is representing the direction. Because red force is towards left, cross is into the board. Now just imagine, this is the rectangular coil, right? I tried to pull it. This is A, this is D. Electrons were traveling randomly, but all of a sudden a force is exerted on the electron into the board. So into the board means from D to A. So all the electrons which were traveling in random direction, now we feel a push or drift from D to A. And when they feel a push or drift from D to A, they will start moving from D to A. Now, when they will start moving from D to A, it will make D at lower potential and A at higher potential. Are you people getting it? Because electrons always travel from low potential to high potential. So can I say the consequence of this FB is actually the motion of electron? And that motion of electron is possible only when one end is higher potential, one end is lower potential. So can I say this FB results in a potential difference? Do you people agree? This FB results in a potential difference because electrons are starting to move from D to A, and electron always travel from low potential to high potential. There is no cell, there is no battery in the circuit. This potential difference, this voltage, this EMF is basically known as induced EMF. This is known as induced EMF. Why we are calling it induced? I'm reminding you again, induction means abnormal. There is no voltage source, but now we can see some EMF across AD. That EMF is known as induced EMF. The current from D to A is known as induced current. So this FB equal EVB, which is into the board, results in potential difference. That potential difference is known as induced EMF. This potential difference results in a current which is known as induced current, which is known as induced current because electrons were traveling in a straight line. The first scientist who actually elaborated all this was Faraday. So the topic we are going to discuss is basically Faraday law of electromagnetic induction. But before that, just tell me one more time. Are you people getting it? How electric current is generated in this coil? When you move the coil, magnetic field sees the electron moving in the magnetic field. It will exert a force. That force causes electron to move in one specific direction. And when electron starts to move in one specific direction, electric current is generated. This current is known as induced current, and the EMF is known as induced EMF. Is it clear till here? How many of you are actually able to understand what I was trying to explain? Yes, Alan, Amna, Maham, Samar.
Sir, I'm still a little confused.
Where are you confused, Maham?
The magnetic force, like the EM force, is basically going into the plane,
Yeah.
and the other force is taking it to the left. So how is it creating a potential difference? I'm confused.
Okay, see, the thing is, for example, let's say this is the coil, right? This is the coil. When I pull it, this is side AB. Electrons are in this side, which are moving in random direction. But when I pull it, this conductor feels a force from this end to this end. So the electron which were traveling in random direction, they experience a drift from side D to side A. So they will move in one specific direction, and that motion is actually the results in current. Because you can relate it the way when we connect battery to the conductor, exactly the same thing happens. The positive terminal of the battery start attracting the electrons in one specific direction. When electron travels in one direction, it generates the electric current. Now I'm getting it. Okay. Now next thing. We need to discuss Faraday law of electromagnetic induction, but using this diagram, I can explain you one more concept that is actually very important for this topic. If we follow this sequence, it should come after 2 or 3 topics, but you can understand it here only. If I look at side AD, initially only force F, red force, is exerted on it, which results a force which is FB, which is AVB. Now, induced current is generated in the conductor AD. The moment current starts to flow in AD, can I say it is a current carrying conductor in a magnetic field? You people may think I can repeat my statement. Once induced current is generated inside AD, can I say it is a current carrying conductor in a magnetic field? How many of you actually agree with this statement? Okay, all of you are getting it. Now, whenever a current carrying conductor is placed in a magnetic field, a force is exerted on that conductor. Do we know what is that force?
ILB sin theta.
ILB sin theta. So there must be a force. I'm calling it F dash. And this is ILB sin theta. By looking at the diagrams, you will surely agree theta is 90. So it will just become ILB. My interest is actually in the direction of this force. If any one of you can tell me the direction of this force. Yes. What should be the direction of this force?
Sir, it will be opposite to the force applied.
Okay, Anas says it is opposite to force applied. So Anas, can I draw it this way?
Yes, sir.
F dash. How many of you actually agree? Okay, some are agree with this direction. Alan, do agree. What about Hania, Maham, Samar? See, it is pretty simple. Finger says downward, current is D to A. So direction technically becomes this, but this is for conventional current. We have electronic current. So direction should be opposite to it. So it will become F dash. So what I can say, I'm trying to pull the coil out of the magnetic field. A force is developed in the coil which try to pull the coil backward into the field. What I'm trying to explain, before that, let me draw the direction here so that I can explain. Now, just imagine, after the class, you may try this thing. Change the direction of this F, red force. Instead of pulling it out, just try to push it into the magnetic field. all the direction will actually get reversed. If this red arrow, instead of left, it is towards right. Let me do it. In this direction, the current which was actually into the board will become out of the board. The current which is into the board will actually become out of the board. F dash, which is actually towards right, will become towards left. Something like this. Do you people agree? If I change the direction of primary force, that is the red one, all the direction will actually get reversed. So what I can conclude, when I try to pull the coil out of magnetic field, the coil wants to move into the field. When I try to push the coil into the field, the coil tries to go out of the field. Can I say this coil is actually opposing the cause, which is producing the induced EMF or induced current? I can repeat my question, then you can think and then answer. The coil always opposes the cause, which has produced induced current in it. Do you agree? Yes, Amna, Mahan, Samar. I mean, if you people are confused, you can just unmute yourself and ask the question. And if you are getting it, you can just raise your hand. Okay, Mahan is getting it. Amna? Amna is getting it. By the way, do I force you people to raise your hand? Because I kept on asking and then all of a sudden you people start raising your hand. If you are getting it, just raise your hand without wasting your time. Because I don't think negative, but sometimes I feel many students join the class, then they keep on doing their work, and when they keep on hearing Sayas is saying Amna, Sayas is saying Maham, they leave everything, they rush to the device and then raise the hand. It can happen, by the way. Anyways, so what I was trying to explain, induced current, make it a little better. Induced current always opposes the cause which has produced it. And why it does this, to obey law of conservation of energy, I will be explaining in later part of this unit. But induced current always opposes the cause which has produced it. The cause of current was you were trying to pull the coil out of the magnetic field. Induced current travels in the direction that ILB tried to push coil into the field. If cause of induced current was the pole which is pushing the coil into the field, now induced current will travel in a direction that will generate a force that will cause the coil to move out of the field. So what we say, induced current always opposes the cause which has produced it, and this is known as Lenz's law. What is Lenz's law? The direction of induced current is such that it opposes the cause which has produced it. And let me do one more thing. Let me highlight this, opposes the cause. Because many students remember that it opposes the induced current. I didn't say opposes the induced current. Direction of induced or opposes the current. Direction of induced current is such that it opposes the cause. What does it mean? I simply made things simple for you by using this coil. But there are a number of ways by which induced current is generated. For example, if it's a coil, you start rotating this coil in a magnetic field. You will surely agree. How many of you have ever owned a bicycle? Okay, that's nice. More than 50% strength used to have a bicycle. How many of you actually have some headlamp or light in that bicycle? So I guess Hania was using top of the line bicycle because it got the headlamp as well. So she put the hand down actually. See, in bicycle we usually have headlamp, but in bicycle we don't have any battery. So you might have observed this thing. To that headlamp there is a wire. That wire is going to the rear wheel. At the rear wheel there are bottle-like structure. When the wheel rotates, the cap actually rotates, and when the cap rotates, it produces electricity and the bulb glow. How many of you have observation like this? You might have experienced or observed this thing in toy cars as well. Normally in toy cars which are not battery operated, when you drag them, their headlamps actually glow. Why? Because in those toy cars there are coils in magnetic field. When we drag them, the coil rotates in the magnetic field. When coil rotates in the magnetic field, induced current is also generated. That's why if you look at generators, if you look at car engine, if you look at generators, you look at anything that is producing electricity, you will be having a sense of rotation in it, that something is actually rotating. How many of you have seen generators actually? Those who actually born and raised in UAE, quite possible they are hearing generator for the very first time. But those who are from Pakistan, India, where load shedding is something very common, they must have seen generators. So Maham and Anas have seen generators. So yes, Anas, what generator was it? Recoil type or that ignition type? If you can elaborate it more.
Sir, I've used both. It was I've used the recoil one also and the switch one also.
Excellent. So remember in recoil type, what used to happen where we pull a rope and we sense that something is rotating in that generator. Remember that?
Yes, sir.
And even this is the same thing which is happening in the ignition as well. So what I'm trying to say, when we talk about rotating a coil in a magnetic field, it produces electric current. It produces electric current. If you go to any cycle shop, you can see those headlamps with which a bottle-like structure is connected. When wheel rotate, that cap rotate, and it produces electricity. You might have seen induction torches. We do have torch lights available in the market operated by batteries, but we do have torches in which there is a lever, you keep on rotating it, and then they will start to glow. What I'm trying to explain, I was actually trying to explain this point, Lenz's law. If cause of induced current is clockwise rotation of the coil, induced current will cause this coil to rotate in anti-clockwise. If cause of induced current is the speeding up of the coil, the induced current will try to slow down the coil. If cause of the current is slowing down of the coil, induced current will try to speed it up. Are you people getting it? That whatever reason we have for the production of induced current will travel in a direction that it can oppose the cause which has produced it. How many of you are actually able to comprehend this point? Yes, Alan, Hania, Amna. Alan, are you there?
Yes, sir, I'm here.
Okay, so are you getting it?
Yes, sir, I'm getting it. Sorry, I couldn't raise the
Okay.
hand. Actually,
Okay.
my kind of broken, so yeah.
Okay, so what you can do, you can use your mic. Now, we were trying to explain Lenz's law. The direction of induced current is always such that it opposes the cause which has produced it. So whenever you will be writing down the equation for induced EMF. In all equation, a minus sign will be there. That minus sign actually refers to Lenz's law. That induced current will always oppose the cause which has actually produced it. Now, let me explain few more things. Let's say we have a solenoid. I hope many of you are actually aware of what is a solenoid. Solenoid is a current carrying coil. Solenoid is a current carrying coil. Good. Let's say this is a rectangular coil. We connect this coil to a voltage source, right? And then we will connect it to a variable Okay, so what I was trying to explain, if we take a solenoid, that solenoid is actually connected to a cell, and to change the current in the circuit, we are actually making use of variable resistor. When current passes through a solenoid, it produces a magnetic field. That magnetic field appears something like, I have drawn these three blue lines are actually magnetic lines of force. The strength of magnetic field produced by a solenoid is given by an equation. This is just for your general knowledge. B is equals to mu naught N I. I hope you remember this mu naught because we did use this mu naught in one of the questions. Permeability of free space. I is the current in the solenoid and N is number of turns per unit length. N means number of turns per unit length. And how will you calculate it? Just calculate total number of turns and divide it by length of the solenoid. Now this whole blue thing is just for your general knowledge. So let me block it so that you can remember. And now come back to the topic. What I did, I took an other coil. That other coil is placed adjacent to the first coil, and I connected this coil to galvanometer. You can use ammeter as well because galvanometer, ammeter are the device that can detect or measure current, right? You can even use voltmeter over here as well. So this is the original setup. Use your common sense. Do we have any voltage source in the green coil or the second coil?
No, sir.
No. So what should be the reading of galvanometer? 0 or non-zero?
0.
0. Galvanometer will be showing you 0 reading. Why? Because there is no current. Now what I will do? I will use this variable resistor, this one. I will change this resistance. This resistance will actually change the value of I. This I actually change the value of magnetic field. And magnetic field actually change the value of magnetic flux. Why? Because I hope we remember magnetic flux is given by B delta A cos theta. Do we remember this equation? Because we did use this formula. Magnetic flux is given by B delta A cos theta. When current in the blue coil changes, the field of blue coil changes, the flux is changed. And when the flux changes, induced current is generated. This is another way of producing induced current. So what is Faraday law? Faraday law says induced EMF is directly proportional to rate of change of flux. Induced EMF is directly proportional to rate of change of flux. Whenever we convert proportionality into equality, we can say we need to put some constant. That constant is basically N. And what is N? N is total number of turns. N is total number of turns. So what is induced EMF? Induced EMF is given by N delta phi over delta T, where EMF is induced EMF, N is the total number of turns, delta phi is flux, and delta phi is change of flux, and delta T is time. So can I say induced EMF is directly proportional to rate of change of flux? The induced EMF stays still the flux is changing and becomes zero when flux becomes constant. Do you agree? I can repeat. Whenever a flux is changed in a coil, induced EMF is generated. This induced EMF lasts till flux is changing and becomes zero as soon as flux becomes constant. Do you people agree? Okay, if we are getting this, that the induced EMF will remain till flux is changing. As soon as the flux becomes constant, there wouldn't be any induced EMF. And all the equations of induced EMF, we will be having a negative sign. This negative sign simply indicates the fact that induced EMF opposes the cause which has actually produced it. Induced EMF opposes the cause which has actually produced it. Now, the type of induction that is happening here, this induction is actually known as mutual induction. Because mutual means in between. Mutual means in between. The kind of induction which is happening in green coil is because of the blue coil. So for this induction, we will be needing two coils. One coil, the blue one, is known as primary, and the green one is known as secondary. The voltage which we are providing in primary is Vp, the current is Ip. All the parameters which are related to primary, we will be using subscript P. The induced current generated will be Is, and the induced EMF generated is Vs. So one thing is for sure, when we change the current of primary coil, magnetic field of primary coil changes. When magnetic field of primary coil changes, the flux of secondary changes. That's why we said EMF is directly proportional to rate of change of flux. If you are getting it, just tell me one thing. Instead of writing this relation, this one, if I write equation like this, induced EMF is directly proportional to rate of change of current in the primary coil. Do you think it is the same thing? You people may think. Instead of saying it is rate of change of flux of the secondary, the green one, if I just say induced EMF is directly proportional to rate of change of current of primary coil, the blue one, it is valid. Because flux is changing, because B is changing, and B is changing because current is changing. So Faraday law can be written in both the formats. You can say induced EMF is directly proportional to rate of change of flux, or induced EMF is directly proportional to rate of change of current. When it comes to a statement, you can state it in any way. You can write this equation in terms of flux. You can write this equation in terms of current. By the way, this induction is called mutual induction. Why? Because you are changing the current in primary coil and induction is happening in the secondary coil. Just think and then answer. Shouldn't induction occur in primary coil as well? My question is, the reasons because of which induction is happening in the green coil, are they not valid for the primary coil as well? Because when current of primary changes, the field of primary changes. When field of primary changes, flux of primary changes. And when flux changes, induced current is generated. So induced current should also generate in the blue coil. That EMF is known as self-induced EMF, and that induction is known as self-induction. Actually, in your syllabus, we don't need to discuss self-induction and mutual induction. You should have this idea only. Whenever you change something which cause a change in magnetic flux, that results in induced EMF. That's it. If it is happening between two coils, it is known as mutual induction. If it is happening in one coil only, this is known as self-induction. Are you people getting it? Yes, Alan, Amna, are you people getting this point?
Yes, sir.
Okay, if you people are getting it, we will be able to solve many questions, because we have to understand few things which you will be in better position to understand when we will be solving questions. Because even if I teach you now, it won't matter, because it will work well when we will be solving question, because there are few graphs that we need to understand, right? So what I'm doing, I'm showing you a question that we may try solving. Okay, this is question number 2. Because we just discussed this whole thing. It's a 6-mark question actually. So all of you should give it a try. Then we will see what points we were supposed to mention here. Are you done? Because your hand is raised actually. Okay, by the way, how many of you were able to answer this question? Okay, Anas did, Hania did, Alan. Okay, see, there are multiple ways with which you can answer this question. One approach could be the way I tried explaining you. If you can elaborate this thing, it's totally fine. Alternatively, what you could have done, see, let's say we have a coil, because question says you are provided with a coil of wire, a bar magnet, and a sensitive ammeter. So let's say this is the coil. It is connected to a sensitive ammeter. We have a bar magnet. This is the bar magnet, right? Now, what we will do, we will move this bar magnet into the coil. We will try to move the bar magnet into the coil. Now, if we are trying to move the bar magnet into the coil, since magnet is coming close to the coil, magnetic field is changing. When field is changing, flux is changing. When flux is changing, induced current is generated. And induced current will flow in a direction, it will oppose the cause which is producing it. So what is the cause? That magnet is going towards solenoid. So if magnet is going towards coil, induced current will try to push the coil backwards. The induced current will try to push the coil backwards. So the direction of current in the coil should be something like this. Do you agree? If I apply right hand rule, remember I did explain you right hand grip rule for a current carrying conductor and a right hand rule for a solenoid. In a current carrying conductor, current always travel in a straight line, right? So thumb indicates the direction of current. Okay, let me turn on my camera so that many of you can see. Okay, it's fine. Remember, if it's a conductor, so thumb is in upward direction, so field is anti-clockwise. When current is in downward direction, thumb is in downward direction, the field is clockwise. I hope you remember this rule. In same lecture, if I'm not wrong, I did explain how to find magnetic field of a current carrying solenoid. Because in a solenoid, current can either move clockwise or anti-clockwise. If current is going clockwise, so thumb is north of the magnetic field. And if it is going like this, right will be north of the magnetic field. Do you people remember? How many of you remember this right hand rule? So what is actually happening here? You are trying to push the bar magnet into the solenoid, right? So what will be happening? Induced current is generated. Induced current will generate in this manner, this green arrow. Why? So that we will be having, in fact, I guess I made a mistake in direction. I will rectify it. So are you getting the direction? How will we find the direction? Now, if you are trying to push the magnet into the solenoid will try to push it back. So the induced current should travel in a direction that will oppose the cause which has produced it. That will oppose the cause which has produced it. So that causes magnet is moving into the solenoid. So induced current will flow like this. Why? If induced current is flowing like this, we will be having a north here. This north of the solenoid will try to repel the magnet. In this question, we don't even need to mention these direction. What we need to mention, because this north-south is something you cannot see. This north-south is something you cannot see. What you can see? Direction of current in the ammeter. So the way I have drawn the direction, the ammeter needle should deflect in this direction. The ammeter needle should deflect in this direction. Just sense the direction of current. Current will move from right to left. The needle will go towards left, right? What if instead of moving the magnet into the solenoid, if I try to pull it back, if I try to pull it back, try to pull it back means this way. No, you are trying to pulling the magnet out of the away from the solenoid. Now current will travel in a direction that south of the magnetic field, south of the coil is here, so that it start attracting it. So the direction of current will actually get reversed. The current will be flowing in this direction now. So needle will deflect in this direction. Are you people getting it? That when we change the direction of motion of the magnet, the direction of current reverses. So in this question, what you will say? You will say, we will connect us the coil of wire with ammeter. We will take bar magnet. We will move north pole towards the magnet and notice the direction of current in ammeter. Now we will change the direction of motion. If previously we were pushing the magnet into the coil, now we will be pulling the magnet out of the coil. The direction of ammeter should change. It will be opposite. It shows that induced current always opposes the cause which has produced it. Direction of induced current will always be in a manner that it opposes the cause which has produced it. How many of you are actually able to comprehend this thing? Okay, I will do try something if I get time. Whatever I have explained, I fill these lines so that you have one consolidated answer in front of you. Otherwise, these were the points which you were actually supposed to mention while answering this question. After this question, okay, so those who got the booklet, this is question number 10, page 134. It's a good question actually, because you will find many questions like this. Once you're done solving it, let me know, we will discuss the answers. Okay, let me solve this question because once I'm done solving this question, what I believe and assume now, after this question, every question that we will be solving, hopefully in next class, you will be able to solve them because we won't be needing anything new to learn. Now just see. Two coils P and Q are placed close to one another as shown in figure 10.1. The current in coil P is constant. An iron rod is inserted into coil P. Explain why during the time that rod is moving, there is a reading in the voltmeter connected to the coil. Now see, the current in the coil P is constant. So magnetic field is constant, magnetic flux is constant. Will induction occur? No. When we put a piece of iron in coil P, it actually changes the magnetic field. How? Because the strength of magnetic field will increase. When field changes, flux changes. When flux changes, induction occur. When induction occur, induced EMF generated, voltmeter will give you the reading. How many of you are getting this answer? Okay, Maham is getting it. Hania getting it. Anas got it. Summer got it. Alan is getting it. Amna? Now, are you getting this answer? By the way, how many of you actually, okay, Amna is also getting it. How many of you are actually were able to solve this question, this graph? Now, listen very carefully what I'm saying. In equation of induced EMF, there is a minus sign. That will always remind you one thing. If current is in positive direction, voltage will be in negative direction. They will be always opposite to each other. They will be always opposite to each other. If one is positive, other is negative, right? Now, question says the current in coil P is now varied as shown in figure 10.2. On figure 10.3, show the variation with time of the reading of the voltmeter connected to coil Q for T equals 0 to T equal T2. Now, number one, the first thing you should have marked this distance. Okay, let me make it dotted so that we can relate it. Because in exam, when this question will be in front of you, if I'm not wrong, both the axes are identical. T1 and T1 are exactly in one line. T2 and T2 are exactly in one line. So this will help you. Drop a perpendicular form here. One perpendicular like this. Why I'm drawing it, I will shortly explain. Other perpendicular form hit. I guess these graphs are not aligned actually. That's why both T1 and T1 are not in one line. So let me draw this way only. What does it mean? On the left of T1 and on the right of T1, you can see a slanted line. There is a slanted line. It has some significance. What is that? I will see. Now see, from 0 to T1, current is increasing. Current is increasing. So it means that current is changing. Remember, rate of change of current results in induced EMF, because I discussed this equation here. Can you see? EMF is directly proportional to rate of change of current. The only difference is we have a negative sign. So when change of current is positive, induced EMF will be negative. Can you see current is increasing? When current is increasing, change of current is positive. So induced EMF should be negative. So you will draw induced EMF on negative axis and you will draw it till here. Why till here? Because during this two dotted line region, if you look at the value of current, the value of current is actually decreasing. The value of current is actually decreasing. So when current is decreasing, change of current is negative. So EMF should be positive. And one more thing that you should have noticed, rate of change of current from 0 to T1 or 0 to that slanted line was less. In green highlighted portion, rate of change of current is large. Why? Because time span is very small and change of current is large. So it means that induced EMF should be large. So induced EMF will be something like this. So this graph will go like this in upward direction. During the time where current is changing, we will be having voltage. It will be go like this. And then in this region, current is constant If current is constant, what does it mean? Change of current will become zero. If change of current will become zero, induced current will become zero. So this graph will drop on this red dotted line, and then it will remain horizontal on time axis. So first, how many of you are actually getting it, what I have done? Yes, how many of you are actually able to comprehend or understand this graph? Okay, if all of you are getting it, it's fine. Because in exam, completing this graph is actually very crucial, because it will be needing some skills actually. You should have this understanding when voltmeter reading should be large, when voltmeter reading should be small, because this gradient is less. So induced voltage is less. This gradient is more, yellow one. So induced EMF is more. When it becomes a constant, induced EMF becomes zero. We need to take care of all these aspects of the graph. So we will resume from here in next class now.